So now let's solve more questions in linear algebra. So this question says two friends, Charles and Bill, both write matrices of order 4 by 4. So each of them is writing a matrix of their own. Let's say what Charles writes, let's call it matrix A. What Bill writes, let's call it matrix B. And both these matrices are of order 4 by 4. Charles writes a symmetric matrix. So it's given that A is symmetric, and Bill writes a skew-symmetric matrix, right? So we know the definitions of what a symmetric and what a skew-symmetric matrix are. So the question here is, for how many matrices does Charles and Bill will get an equal matrix on comparison? For these two matrices to be equal, every element of the 4 cross 4 matrix should be same, right? So the question here is, how many such matrices exist such that A is symmetric and B is skew-symmetric such that A equals to B? Bottom line, that's the question. The Charles and Bill is the story around it. Okay, so let's actually solve this problem. So very simple. So you're given that matrix A is symmetric, which means A transpose equal to A, and you're given that B is skew-symmetric, which means B transpose equals to minus B. Very simple stuff, nothing very fancy. Now I can follow a bunch of equations here and solve it, okay, and show what are the possible values of A and B. First, let's assume, because we are given that they both got an equal matrix. They both, so what is given here is that A is equal to B. The question here is, if A equals to B, how many possible values exist for A and B, right? So simple question. So since A equals to B, okay, so this is already given to us, and the properties that are given to us are A transpose equals to A and B transpose equals to minus B. Okay, if this is true, then if I take transpose on both sides, I would get this. And because A transpose equals to A, because A is a symmetric matrix, and since B is a skew-symmetric matrix, this follows. So I'm just using what is given to me. What is given to me is that A is symmetric, B is skew-symmetric, and A equals to B. Okay, so this also implies this. If this is so, I can bring my B to the other side, which means A plus B equals to 0. Right? Since A is equal to B, 2A equals to 0. When will 2A be equal to the matrix 0? Only when A matrix equals to 0. Right? So there is only one matrix which such that there is only one matrix. There is only one matrix where all the elements are 0. Again, I'm just writing 1 0 here to represent that this is a big 4 by 4 matrix where all the elements are 0. Only when Charles has picked up the 0 matrix and Bill has picked up the 0 matrix, you would have a situation where A is equal to A transpose and B is or minus B equals to B transpose and A equals to B. There is only one. So these are the three equations that are given to us to state that A is symmetric, B is skew-symmetric, and A equals to B. The only matrix that satisfies these conditions is A equals to B equals to a 0 matrix. So there is only one. So the answer for this is there is only one matrix, which is the 0 matrix, which satisfies these conditions. Okay, very, very simple. There is another way to think about it, which is, look at this, A equals to A transpose minus B equals to B transpose, and A has to be equal to B, right? So if A equals to B, if I just follow these rules, right? If I just follow these rules, A equals to A transpose, right? Which is equal to B transpose, right? Because A and B are equivalent, right? Or in other words, I can also write this as, so B transpose, I can write it as minus B, which I can write it as minus A. When will A be equal to minus A? Only when each of the elements of A are equal to 0. This is another sequence of steps that I can take. Again, this is effectively doing the same thing, right? What this is doing is basically A plus A equals to 0. But instead of going through these steps, you can very intuitively also argue that given these three equations, you'll end up with a situation where A equals to minus A, which is only true when each of the elements of A is equal to 0, because only 0 equals to minus 0. Okay, so very simple question, straightforward question here. Now let's go to the next question. This is a more interesting one. Okay, so the question says, consider the matrix P as P11 and P12 and P21 equals to 1. So this is what you'll have, and P22 equals to minus P11. Okay, so if you just use this, P11 equals to 1, P12 equals to 1, P21 equals to 1 and P22 equals to minus P11. So this is what your P matrix will look like. It's a simple 2 cross 2 matrix. Now the question here is, let Q be the matrix that you obtain by performing the sum of P, P square, P cube, so on, P power 20. The question here is, what is the trace of Q? Right? The question here is not what is the value of Q, but what is the trace of Q? Trace basically means I only care about the diagonal elements. I don't care about the non-diagonal elements. Okay, so let's actually see the pattern here. So given that we are given P, see whenever you have this, right, let's try and find patterns in these. So if you compute P square, again, since this is a 2 cross 2 matrix, it's very simple to compute it. The 2 cross 2 matrix has 2 0 0 2. Okay, seems to make, see here you have 2, it makes sense. What about P cube? So you computed P square. When you compute P cube, what you get is 2 2 2 minus 2. If you notice P power 1, look at this, P power 1 and P power 3 have this nice pattern. P square has non-diagonal elements as 0, but the diagonal elements same as this. Let's look at P power 4 also and come up with some pattern here. See, because you have to sum up till P power 20, we'll have to come up with some pattern. Now if you look at P power 4, to compute P power 4, you can just multiply P square with itself. Again, if you look at P power 4, you're getting 4 on the diagonal elements and the non-zero elements, non-diagonal elements are 0. So by just looking at P1, P2, P3, P4 or P power 1, P power 2, P power 3 and P power 4, you can come up with a nice formula for this. Okay, again, this is not rocket science, this is very doable. Okay, so okay, let's go with this, right? So again, you can keep, if you're not convinced with these formulae, you can also compute P power 5 and P power 6 and convince yourself that these formulae are true, right? So P power n is 2 power n by 2 on the diagonal elements and 0 on the non-diagonal. If n is even, look at this, we have a different pattern when n is even, like 4, and a different pattern when n is odd, right? When n is odd, you have 2 power n minus 1 by 2 here and the negative of that number here, and the same number repeats here. This is also true when n equals to 1, right? So when n equals to even, you have one pattern for P power n. When n equals to odd, you have the other pattern. Now the interesting part here is you're asked what is the trace of Q. Now you're given that Q equals to P plus P square plus P cube, so on so forth up to P power 20, right? Trace is basically the sum of the diagonal elements. So trace of Q would be the sum of traces of all of them. So this equation also holds true. It's a straightforward equation. Remember that it's a straightforward equation, right? Because you're just operating on the diagonal elements themselves. Now comes the fun part. Okay. If you look at whenever n is odd, when I add these two elements to compute the trace of that, these two would cancel out and it would become 0, right? When n is even, these two will sum up and it would become 2 power n, right? Because you have 2 power n by 2 plus 2 power n by 2, right? This is what you have. You have 2 power n by 2 plus 2 power n by 2, right? So when you add these two things up, look at this, you'll get 2 into 2 power n by 2. Or in other words, 2 power n by 2 plus 1, if you want to write it this way. Remember that this is not 2 power n. Okay, that's a mistake because this is not multiplication, this is addition. Okay, this is one mistake that some people may commit. Okay, but don't worry about it, we'll write it in this form so as to avoid any confusion. So if you look at it, the odd terms will become 0. The traces of all the odd terms will become 0. The traces of even terms, look at this. This is what will happen when you have trace of P square. If you notice trace of P square, for P square what did we have? We have 2 0 0 2. So it is 2 times 2. For P power 3, this is 0. For P power 4, if you notice for P power 4 what do we have? We have 2 into 2 square and so on and so forth. So if you sum up all these elements, because the odd ones will become 0, only the even ones will survive, you can write this summation. You can write this summation very easily as this. From here onwards, it's a very simple algebra, right? So you can write this as 2 into, look at this, I'm taking this 2 out, 2 plus 2 square plus so on up to 2 power 10. Now this is a very simple addition. This is basically an arithmetic progression, right? If you think about it, you can write this as an arithmetic progression. So you have the 2 outside, you have this 2 here, 2 power 10 minus 1 by 2 minus 1. Okay, so if you simplify this, again, this is also very simple to compute. If you write this as, if you take both 2 and 2 outside, if you remove this 2 also outside, you will get 1 plus 2 power 1 plus so on up to 2 power 9. Right? And we know 2 power 0 up to 2 power 9 is nothing but 2 power 10 minus 1, which is nothing but 1023. And 2 into 2 is 4. Again, even if you have forgotten this arithmetic progression type of formulae, from simple, as a computer science student, you have to understand the sum of squares of 2, because this is so often, this occurs so often in computer science, right? 2 power 0 plus 2 power 1 up to, so if you have 2 power 0 plus 2 power 1 up to so on so forth 2 power n minus 1, this is equal to 2 power n minus 1. Right? Again, you can prove this logically using the arithmetic progression type of formula, but this is a very simple thing that we all almost know it as computer science students. Right? Even for the non-computer science students, you could have just used the arithmetic progression formula and you could arrive at 4092. Nothing fancy here. The only tricky part here is to recognize this formula. Okay, the only challenging part or the non-trivial part here is to recognize this form of p power n when n is even and this form of p power n when n is odd. Once you get this, rest of the math is very, very straightforward. Okay, so let's go to the next question. Okay, so consider the following statements. Eigenvalues of involutory matrix are 0 and 1. So first of all, what is an involutory matrix? For those of you who have forgotten what an involutory matrix is, an involutory matrix is a matrix where A into A is identity matrix, or in other words, A inverse is A itself. Okay, so it says eigenvalues of an involutory matrix are 0 and 1. So let's actually see that. Okay, so if I take det on both sides, okay, if I take det on both sides, what happens? Det of A square equals to 1, right? And we know the product of eigenvalues. We know that the product of eigenvalues is equal to the det of the matrix. Okay, that's why I've taken det on both sides. Now, what will be the values of det of A now? If det of A square equals to 1, det of A can either be plus or minus 1. Right? If my det of A is plus or minus 1, my eigenvalues got to be plus or minus 1. Right? So it cannot have an eigenvalue which is 0. So this statement is incorrect. Right? Now, as soon as this statement is incorrect, A cannot be the answer, C cannot be the answer. Right? Now you have to worry only about whether B is true or whether 2 is true or 3 is true. Okay, so I'm just removing some of these options so that I'm seeing if I even have to read these two options. The geometric multiplicity of an eigenvalue should not be less than its algebraic multiplicity. Imagine that you don't know this concept. Okay, again, this is one of the concepts that we have not covered in the course videos, but don't worry about it. Imagine you don't know this. Okay, we want you to be prepared even for those situations, because the concepts of geometric multiplicity and arithmetic multiplicity have never been asked in GATE, hence we did not cover it. Okay, imagine first time some other new concept is given. Then look at this third option. The third option says, okay, so this we don't know. We don't know about this. Let's keep it there. It's okay. So what is the third statement saying? Elementary row or column operations performed on a matrix does not change the row or column rank of the matrix. We know that this is true. Right? We know that this is true. Right? To compute the rank of a matrix, if I use elementary row operations or elementary column operations, the row / column rank will not change. So this I know is for sure true. So see, since A is not true, C is not true, either B is true or D is true, and we know for sure D is true. Right? So option D is the right option here. And of course, it might, so just because a concept has never been asked in GATE does not mean that it may not be asked. But that does not mean that we have to cover everything that is there in linear algebra, because linear algebra is a fairly large subject. We could spend 100+ hours just doing linear algebra. Okay, so it's a trade-off that we have to work under. Okay, so I hope you got to understand how to tackle problems when you don't know a concept, which would happen to anyone for that matter. Okay, so let's go to the next question. Okay, so the next question says, for what values of h the following vectors are linearly independent? Okay, so you're given 3 vectors here. There is no h here, there are 2 h here, there is h here. Now for these 3 vectors, remember that these are 3-dimensional vectors. These are vectors in 3D space, right? For these 3 vectors to be linearly independent, right, one simple technique I can employ is, if I write this as column vectors, right? If I write this as column vectors, right? Right? See, what is det of this matrix now? See, I wrote this as basically column vectors. What is the det of this? Det of this we saw is the volume of the parallelepiped. See, again, I'm coming from geometry here. What is the volume? So when are they linearly independent? Okay, when the volume of these three vectors, let's assume these are three vectors in some 3D space. If the volume created by three of them is not equal to 0, then they are linearly independent. Right? That's the logic here, right? And how can I compute the volume? By taking the det. Right? Very simple concept. So linear independence is connected to the volume, and volume itself is connected to the concept of determinant of this matrix which you're constructing. So I can write this as, because you want them to be linearly independent and we want to find the values of h which will make it linearly independent, I'll just construct this matrix with each of these as 3 columns, right? And this matrix should be non-singular, or in other words, the det of this matrix should not be equal to 0. Now let's try to simplify it. Since these two are 0, we don't have to worry about them. This whole thing will boil down to this form. Okay, again, look at the form that I'm trying to get this into. I'm trying to get this into some multiplicative form which is not equal to 0, so that I can easily get the values of h. Right? So let me just scroll down a little so that this is clearer. Okay. So I'm trying to get this into a multiplicative form here. Look at this. When I'm simplifying this determinant, I'm trying to get this into a multiplicative form so that I can say that h should not be equal to -12 and h should not be equal to -1, because the moment they become equal to -12 or -1, this whole thing will become 0 and the matrix and these vectors will now become linearly dependent, which we don't want. Right? Now if you look at all the options that are given to us, we are given 4 options, right? So it cannot be equal to -5 and it cannot be equal to -1, right? So it cannot be equal to these 2 values. It can be any other value. Now amongst the 4 options that you're given, which option makes the most sense? Right? If you look at this, see, this says -5. The moment you have 0.5, this cannot be the answer. Here from R, you're subtracting this whole range. There is no need to subtract the whole range itself. Okay, look at this. You're subtracting the whole range here. You don't have to subtract the whole range. The right answer here is R minus a set that you'll construct with just -12 and -1. See, for example, this could have taken -0.7. If h equals to -0.7, there is no problem, right? But here, look at this form. This says R minus the set of values between -0.5 and -1, right? So because this is the range, this is not a set. The ideal way of writing it is in this form, wherein you're saying R can be any number except the numbers that are there in this set. And this set consists of only 2 numbers, -0.5 and -1. While when you write it this way, you're saying all the numbers that lie between -0.5 and -1, including those 2 numbers. So the right option here is option D, because none of these are the right options. This is how, instead of these square braces, if there were curly braces here, this would have been the answer. Right? I hope this is clear. Now let's go to the next question. Right? The next question says, consider a real matrix A. So all the values have to be real, and you have this A here, A here, A here. Rest of the values are given to you. And you're decomposing this matrix A into a product of 2 matrices L and U, where L is the lower triangular matrix, U is the upper triangular matrix, and det of U equals to 191. Then what are the possible matrices for A? Basically, if you know what are all the possible values of A, right, then you can say how many possible matrices A are possible. Now one thing you have to remember here is when we wrote A as a product of lower triangular and upper triangular matrix, if you recall, we wrote the lower triangular matrix as having diagonal values 0, right? All the upper triangular values were 0 anyway. So these ones were L21, L31, L32. If this is a 3 cross 3 matrix, of course it has to be a 3 cross 3 matrix because A itself is a 3 cross 3 matrix, right? While on the other hand, for U, we did not limit U's diagonal elements, right? So we said U22, U33. This is all 0, but this is U12, U13, U23. So one thing that you have to notice here is for the lower triangular matrix, we use the values of 1 here. That's a very, very important thing when we discussed LU decomposition in the course videos. But for the upper triangular matrix, these values need not be 1. Right? When you do this, look at this, A equals to LU. So det of A should be equal to det of L into det of U. Right? Because again, why am I using dets here? Because I'm given det of U. Because I'm given this value, I'm trying to use that. So this det is equal to 191. What about this det? Because this value is 1. 1 into this value is going to be 1. Right? This value is going to be 0. So det of this matrix, det of a lower triangular matrix with all the diagonal elements equal to 1 will be equal to 1 itself. You can verify this, by the way. When you're computing the det, right, take this. This is 1 minus 0. This is 0. So everything will be 0. This is 0. So everything will be 0. So if you try to compute the det of this matrix, it will be equal to 1. So det of A now det of A is equal to 1 into 191. This is not det of 9. This is 191. Okay. There is no concept of det of 9. Makes no sense. Right. So now what is given to us? Det of A is equal to 191. Okay. So let's compute the det of A. I can represent det of A as an equation in my variable A that I have here. Right. So let's solve it. Again, I have solved it already here. So let's go through it. Okay. Actually, you don't even have to worry about it. So the better way is actually, again, we have just tried. So when you say det of A equals to 191, right? When you simplify the equation, you'll get a cubic equation because A is a 3 cross 3 matrix. You'll get a cubic equation of this sort. And we just tried what values of A will satisfy this. What real values of A will satisfy. Okay, that's very, very important, right? Because you're given that matrix A is a real matrix, not an imaginary or complex matrix, right? So since A is a real matrix, we wanted to find out which real values of A will have this equation valid. And by just simple trial and error, we found that A equals to 7. Of course, we didn't have to resort to trial and error. We could have decomposed this into a quadratic equation multiplied by a linear equation and all of that stuff. But we just, for speed, we just tried trial and error, and we got only one real value for A, where A equals to 7. Right? And this is the only real valued root. The rest of the roots are complex. Right? So the number of real matrices possible is only 1, because the variable small a or lowercase a has only one possible value, which is 7. Right? Since the question says how many possible values, how many possible matrices exists for capital A, since small a or lowercase a can only take one value, which is 7, there is only one possible matrix, and hence the answer is 1.